Great. So, hello everyone. We're happy to have Lyne Moser from University of Regensburg, who will be speaking about new methods to construct model categories.
Okay, yeah, thank you for the introduction and so for the opportunity to speak in the seminar. So as you say, I want to talk about new methods to construct model categories, and this is going to be joint work with Leonard Guetta and Sarazola and Paula Verdugo. And just a few things I'd like to mention. First of all, I put a link in the chat for the slides of the talk. If you want to take notes directly on the slides, it might be useful, and you can just download it from there. And the other thing is, if you have any questions during the talk, please feel free to interrupt me. I'd be very happy to answer them. Okay, so let me start with some background on model categories. And I want to start with some motivation first. So model categories, they were introduced by Quillen, and they provide a nice framework to do homotopy theory. And so when we do homotopy theory, what we want to do is like study when two objects, let's say algebraic or geometric, are the same. And by this, I mean that I have an appropriate morphisms between my objects, which may, for example, like preserve the algebraic or the geometric structure. And I want them to be appropriately invertible. And let me give you some examples for this. And so maybe one example, which is a bit boring, but from a homotopical point of view, is that of sets. So maybe I want to study sets, and I want to say when two sets are isomorphic. And so when I say appropriate morphisms, what I mean is like a map of sets, and then appropriately invertible in this case would be a bijection. But as I said, this is not very interesting from a homotopy theoretic point of view, because already in a category, you capture the notion of isomorphisms and so bijections. So maybe more interestingly, you have topological spaces. And a good notion of map between two topological spaces is that is a map that preserves the topology, so a continuous map. And maybe we want to study when two topological spaces are weakly equivalent. And by this, I mean that all of their homotopy groups are isomorphic. And so this is one of the motivating examples that Quillen was looking into to define these model categories. But the other one came from algebra and is that of a chain complex of R modules. So if you start with two chain complexes of R modules, then you have a good notion of maps between them, which is a chain maps. And then you can ask yourself, when are two chain complexes quasi-isomorphic? Namely, when do they have the same homology? So when are their homology groups isomorphic? And so the idea was that like model categories kind of unify these two types of frameworks, so homotopy theory and homological algebra into one framework. And we can study this more abstractly in this context of model categories. And I'd like to mention one last example, which is going to be of interest in the talk, and it's that of categories. And so between categories, I have a notion of morphisms, which is that of a functor. And then I can ask myself, when are two categories equivalent? And this is maybe the notion of invertible morphism that I'd like to consider. And so all of these invertible morphisms, they will be the main players in a model category, and they will be called weak equivalences. And these are the maps that we would like to invert in order to understand when two objects are the same. And so to any model category, you can associate a homotopy category where these weak equivalences will become the isomorphisms instead. So as I said, they are the main players, but they are not the only structure that you have in a model category. And actually, you have some extra structure than the weak equivalences in a model category. And this structure is there in order to actually make computations. So for example, like I said, like to a model category, there's an associated homotopy category, and this extra structure kind of gives you a way of computing this homotopy category. But also it allows you to do other type of computations. So for example, you can explicitly compute the derived functors using this additional structure, such as homotopy limits or homotopy colimits or other functors that you would have in mind. And so these are like these functors that descend to the homotopy categories. And in particular, they will preserve, like, I mean, they would say send weakly equivalent objects to the same thing. So they will preserve weak equivalences. And another thing that you can do, for example, is like approximate objects with better behaved ones. And for this, I want you to think, for example, if I have a topological space, and I'd like to find a homotopy equivalent space, which is a CW complex instead. So this would be one type of approximation that I can do in a model structure, CW approximation. The other example, maybe more algebraic, is if you start with an R module and then you want to compute its projective resolution, this could also be done, for example, in a model structure. So these are the type of approximations of objects that I want to mention. And we will see a bit more abstractly what I mean by this in a moment. And the last thing that I'd like to mention, because it's getting more and more important these days, is that every model category has an underlying infinity category. And so typically having model categories allows you to construct such homotopy covariant structures. But having the model category also allows you, for example, to give explicit models for the home spaces of your infinity categories or this kind of things. So this is kind of for the motivation for this like extra structure that we have in addition to the weak equivalences. And as I said, like we have weak equivalences, we have an extra structure, and then like there are lots of axioms that like a model category satisfy. And this makes it into a very robust structure. And so in particular, building a model structure in practice is really hard. And this is where like this project came into place, because we want to understand, we want to find methods to build model categories. And so we want to have some conditions that are checkable in practice that we can use to build model structure on certain categories. Okay, so this was for the motivation part. And now I'd like to move on to the definition. So model category, model structure is going to be a structure that you put on a certain category, which is both complete and co-complete, by which I mean that it has all small limits and all small colimits. And before defining a model category, I'd like first to define what a weak factorization system is. So a weak factorization system, which I will abbreviate in the talk as just WFS, is going to be a pair of classes of morphisms, which I denote by L and R for left and right. And the requirement, first of all, that these classes are closed-order retracts. And then you have two different axioms that you need to satisfy. So one of them is that whenever I start with a commutative square in my category, such that the left-hand map is in my left class and the right-hand map is in my right class, then I can find a lift in this square, by which I mean a map from B to X, making both of the triangles commute. And the second axiom requires that whenever I have a morphism in my category, I can factor it into a map in my left class, followed by a map in my right class. And so in particular, it's kind of an easy exercise to show that my left class is actually fully determined by a certain lifting property against my right class. And I will denote like this, the class of maps in M, which have the left lifting property against all maps in R. So by which I mean that whenever I have a commutative square like this, where the left-hand map is F and my right-hand map is any map in R, then I can find a left like this. And so the left class is determined by having this lifting property against all maps in R. And similarly, the right class is determined by having this lifting property against all map in L, but on the other side this time. So the right lifting property instead. And so in particular, what we see is that in a weak factorization system, giving the left class or the right class fully determines the other by this lifting property. So the left and right class fully determine each other. Okay, so this was for a weak factorization system. And now I'd like to give the definition of a model structure. So a model structure is going to be this time a triple of morphisms, of classes of morphisms in M. So as I said, like we have this class of weak equivalences, which are the maps that we would like to invert at some point. And so they are going to be denoted by W. But then we have two other classes, which are the cofibrations and the fibrations. And so the weak equivalences will be denoted by this like tilde, and then the cofibration with a hook, and the trivial fibration with this double head arrow. And I also want to introduce more terminology. So if I have a cofibration that is also weak equivalence, I will call this a trivial cofibration. And if I have a fibration that's also weak equivalence, I will call this a trivial fibration. And so a model category satisfies two different axioms. And the first one is the requirement that the class of weak equivalences is a class of invertible maps, or like behaves as a class of invertible maps. And so what we want to require is that the class W is closed under 2 out of 3. And so what is this 2 out of 3 condition? It tells you that whenever you start with two composable morphisms, F and G, and any of the 3 maps, F, G, or the composite, GF, are in the class of weak equivalences, then so is the third. And typically, this is something that you can check quite easily, that is easily satisfied by isomorphisms typically, and you can also check them for the other classes of weak equivalences that I gave before. So this is something very natural to ask for a class of invertible maps. And the second condition is the requirement that we have two different weak factorization systems. And the first one is given by that of cofibrations and trivial fibrations. And the second one is trivial cofibrations and fibrations. So we want that each of these pairs satisfy the axioms of a weak factorization system. And so in particular, before we say that in a factorization system, the left class determines the right class and the right class determines the left class. And so in particular, if I look, for example, just the class of weak equivalences and cofibrations, say, then I can determine my class of fibrations by the class of trivial cofibrations, so the intersection of these two classes. So typically, just giving weak equivalences and cofibrations already determine the model structure. And this is also true if I take weak equivalences and trivial fibrations, or weak equivalences and fibrations, and weak equivalences and trivial cofibrations. So any of these two classes already determine my model structure. And by which I mean that if I have two model structures which have these classes in common, then they have to be the same. So any questions about the definition? Okay. So let me give some examples of model structures. Maybe I will start with the non-interesting example. So if I look at the category of sets and maps of sets, then this is a complete and co-complete category. And I can put a model structure on that category where the weak equivalences are the bijections, as we had before, and the cofibrations are all maps. And actually, this is a model structure that you can put on any category, and it's called the trivial model structure. And this comes from the fact that the class of all maps and then isomorphisms, or conversely, isomorphisms and all maps, they form weak factorization system in any category. And maybe this is kind of an exercise.
Can I ask a question about your remark?
Yes.
Is it true that you can also, like, just because the pairs you listed all incorporate the weak equivalences, can't like you have the pair just like see it like cofibrations and fibrations and determine the
I mean, we will see in a bit that it's almost enough, but
okay.
But like, it's not obvious from like what I said so far, because I'm really using the fact that I have this weak factorization system and that the left class determines the right class and so on to say this statement. And the statement that you're saying is a bit more difficult to prove, but it's resolved by Joyal. Yes.
Okay.
And actually, it will be even less than this, but we'll see in a bit. So yeah, I'll come back to this. Okay, so this is for the first example. And the second example is this categorical example that I was telling you about. So if I look at the category of categories and functors, then I can define a model structure where the weak equivalences are the equivalences of categories, and the trivial fibrations are the surjective equivalences. And by this, I mean that there are these equivalences of categories that are surjective on objects, rather than just like essentially surjective on objects. So these are some examples of model structures. And of course, you have a model structure for topological spaces and a model structure for chain complexes. And actually, there are many more now in the literature also. But these are the ones that I wanted to present for this talk. Okay, so before I go into constructing model categories, I'd like to mention two other things. And the first one is combinatoriality. So this is kind of a size issue condition. So we want that when we build model structures, the categories that we build model structure on are not too big, and the weak factorizations are not too big as well. And so this is kind of like what this condition is about on a model category. And it's very useful in practice. And in fact, it's often the case that like a model category is combinatorial. So for this, I first need to introduce what it means to be cofibrantly generated for a weak factorization system. So it's going to be cofibrantly generated if there is a set rather than a class of maps in my category, such that the right class of my weak factorization system is determined by the right lifting property against this set. And so in practice, this is useful because then you just have a bunch of maps to check the lifting property against, rather than just a whole class, a whole abstract class. And the second, and so then we can define, a model category to be a combinatorial if, first of all, the category M is locally presentable. So if you don't know what this means, it's just, again, some size condition issues. So like, we don't want it to be too big, basically. And both factorization systems are cofibrant.
Lynn, I think you froze for maybe 10 seconds.
Oh,
And
okay.
my computer. I don't know if people had that issue. Yeah. So it
Yeah,
was
I think it says my connection is unstable. I'm sorry.
no worries. Yeah. It was you were explaining the definition of combinatorial when you froze.
Okay, yeah, I'll go back to this. No worries. Thank you. Okay, so I was saying that a model category is combinatorial if, first of all, the category on which we put the model structure is locally presentable. And this is just some size issue condition. So you just don't want M to be too big. It's not very important if you don't know what this means. Just like take it as we don't want M to be too big. And the other condition is that both weak factorization system of the model category are cofibrantly generated by sets I and J. Okay. So, and the other thing that I want to mention, which I already mentioned a bit in the introduction, is the approximation of objects. And so if we are in a model category, because the category that we build the model structure on is complete, it has in particular a terminal object. And so I will denote this terminal object by the star. And then we say that an object is fibrant if the unique map to the terminal object is a fibration. And these are usually the well-behaved objects in a model category, at least in the more geometric settings. And so they form a very important class of objects. And in fact, to go back to what Sophia asked before, there's a theorem by Royal, which is that having just the cofibrations and the fibrant objects already determines the model structure. So if I'm given this class of cofibration and the class of fibrant objects, I can retrieve what the weak equivalences are from just these two classes. And then you already know that if two model structures have the same cofibrations and fibrant objects, then they are the same. And of course, because of the weak factorization system trick, it also works if you replace cofibrations with trivial fibrations instead. So it's even less than cofibrations and fibrations, just cofibration and fibrant objects are even enough to already determine the model structure. And in particular, we'd like to, we say fibrant objects are the well-behaved ones. So we would like to see if we can approximate any objects with a fibrant one. And this is called the fibrant replacement or fibrant approximation. And this is going to be a weak equivalence where like the target is fibrant. So if I start with an object X, I want to find an object S prime, which is fibrant and equivalent to it. And in fact, you can always do this because fibrant replacement in a model category always exists. And the way to see this is by using this weak factorization system of trivial cofibrations and fibrations. And then you can look at this unique map to the point. And we say that in a factorization system, you can always factor any map into a map in the left class, followed by a map in the right class. And so by factorizing this map into a trivial cofibration followed by a fibration, I get one possible fibrant replacement of my object. Okay, so what we want to keep from this this approximation of objects is that, like, first of all, every object is weakly equivalent to a fibrant one. So and the second thing is that since I can always fibrantly replace an object, actually, like, to determine whether a map is a weak equivalence, I can also determine it after having done a fibrant replacement. And so kind of like knowing what's happening between the fibrant objects already kind of determine the model structure. So this is kind of the approach that we'll be taking when we build model structures. We know what the fibrant objects are, we know what the weak equivalences between fibrant objects are, and then we can kind of build a model structure just from these data. And this is kind of like the goal of the methods that we developed. Okay, so this was for the model categorical background. I don't know if there are any questions. Okay, if not, I'll move on to the construction of model structures. So first I'd like to recall a method that is like almost as old as model categories, I think, and it's that of right-induction. So the idea of right-induction is that you start with a model structure on a certain category N, and let's call it a W bar, C bar, F bar. And then you have another category M on which you'd like to put a model structure. And this comes equipped with an adjunction to N, the category that has a model structure, where the right adjoint points from M to N. And so what I would like to do is build a model structure on M from that on N. And so this is called the right-induced model structure. And if it exists, it's gonna have as weak equivalences, the one that was image under this right adjoints are weak equivalences in N. And the fibrations are going to be the pre-image of the fibrations in N. And so in particular, you can see that like trivial fibrations, which are just the intersection of the fibrations and the weak equivalences, are going to be the pre-image of the trivial fibrations again. And so, as I said, like right-induced model structure might not always exist. And there has been a lot of results in the literature, which shows like when or like what kind of condition you need to show in order for them to exist. And I want to mention one of them, which is like going to be useful to compare to the methods that we developed in afterwards. And it states as follows. So first, there are some, again, size control conditions. So we require that N is combinatorial and M is locally presentable. So we just don't want N and M to be too big, basically. And then one can show that the right-induced model structure on M exists, and it's going to be, again, combinatorial if the following conditions hold. So the first condition is some existence of path objects condition. So it says the following. So whenever I have an object in M, which is going to be one of the fibrant objects, so by which I mean that its image under the right adjoint is fibrant in N, then I can factorize the diagonal at X into a map that's going to be sent to weak equivalences, followed by a map that's going to be sent to a fibration. So basically, we're saying that we can factor the diagonal into weak equivalence followed by a fibration. And this is exactly what path objects are about. And then the second condition is the existence of functorial fibrant replacement. Basically. And it says the following. So every time I have an object, I can find a map which is going to be sent to weak equivalence such that the target is going to be fibrant. So it's going to be sent to a fibrant object. And I just don't want to have like these fibrant replacements, but I also want them to be functorial in X. And if you compare to what I said before, this is really what a fibrant replacement in M should be, because it's a weak equivalence to a fibrant object.
Lynn, I have a question. So
Yes.
is for left induced, is the result completely dual, or are there any subtleties I have to be aware of?
No, it's completely dual, and it's in the paper by Hess, Kedzierek, and Shipley. And basically, you replace this path object by the cylinder object, and this fibrant replacements by cofibrant replacements, I think, yeah. But I think it works as well, yeah. Okay. And so, as I said, like right induction might not always work, and I will give you a counterexample where it actually doesn't work. And for this, I need to introduce some terminology first. So a double category is going to be an internal category to categories. And by this, I mean a diagram of the following form. So I have a category of objects, and then I have a category of morphisms. And then I have source, target, and identity maps, like you would have for a category, which are actually functors between these categories. And also a composition map, which takes two morphisms and send them to the composite, and then like the extra data in the category also to composites. And I'm requiring that this composition is both associative and unital. So if you look at what the category objects in set is, it's just a category, and then a category in categories is a double category. And in particular, I can actually extend this diagram into a simplicial diagram in categories. And for example, here I have also other maps from this pullback where like I can take the projection maps onto A1, and then I can extend this further on the right-hand side by adding more and more copies of these A1s here. So from just this diagram, I can form a diagram like this, which looks like a nerve diagram, right? And so this gives me an inclusion of double categories into simplicial objects in categories, which I call N for nerve, and it admits a left adjoint C. So now I am in the setting of this like right-induction theorem because I have two categories and an adjunction between them. And here I told you before that I have a model structure on the category of categories, which is the canonical model structure. And I can actually put a model structure on the functor categories, which is the ready model structure because delta is a ready category. And if you don't know what this is, it's not very important for the talk, but this is just a way of producing model categories on functor categories, basically. And so what Fiore, Pronk, and Pauli showed is that the right-induced model structure on double categories actually does not exist. And the problem is not about the path object. This works well. The problem is that like these fibrant replacements are not necessarily, that these fibrant replacements just don't exist. And the problem is that you can find some push-outs of trivial cofibrations that are not weak equivalences, basically. And so this shows that like there are some cases where right-induction doesn't work. And this is where we're starting to ask ourselves, is there a weaker way of inducing a model structure along an adjunction that would give more examples in practice? And so we call this fibrant induction. And everything I'm gonna say now is a joint work with Guetta, Sarazola, and Verdugo. And so we start exactly as before. So we start with a model category and we start with an adjunction as before. And just to remind you, like the right-induced model structure was defined by inducing all weak equivalences and all fibrations. But now what we want to do instead is still induce weak equivalences and fibrations, but instead of inducing all of them, we just want to induce them between fibrant objects. And this is kind of the idea of what's gonna happen now. And so before the trivial fibrations were also the induced one, and this we are going to keep. So we call this fibrantly induced model structure. And so as I said, the trivial fibrations are still going to be the induced one, but now we're just going to induce the fibrant objects. So something is going to be fibrant if and only if its image is fibrant. And as I was telling you at some point, trivial fibrations and fibrant objects already determine a model structure. So if this model structure exists, it's unique. And moreover, we can see that the trivial fibrations here and here are the same, and the fibrant objects here and here are going to be the same as well. So in fact, if the right-induced model structure exists, then it has to coincide with the fibrantly induced one. But maybe the right-induced model structure doesn't exist and the fibrantly induced one still exists. So this could happen. Okay. And so before we had a theorem which was telling us when the right-induced model structure exists, and we had some path object condition and some factorial fibrant replacement condition. And we kind of want to find a similar theorem here in this case of fibrantly induced model structure where this would also happen. And so we start with the same condition as before. So we want N to be combinatorial and M to be locally presentable. And then we will have the existence of this fibrantly induced model structure if the following conditions hold. So first of all, this condition stays exactly the same. So we still have this existence of path object condition. So it's exactly the same as before. So for every object X, such that its image is fibrant, I can factor the diagonal into weak equivalence followed by a fibration. But then the second conditions, now it's kind of becoming trivial because of the way that we define the model structure. And by this, I mean that the following. So because we have something combinatorial and something locally presentable, we can actually show that the pair of the following pair of classes in M form a weak factorization system. So here I have this class of like the preimage of the fibration on the right-hand side, and on the left-hand side is whatever class is determined by it. And this is a weak factorization system, which is cofibrantly generated by the image under the left adjoint of the generating set of trivial cofibrations for N. So J here is like the set that determines this fibrations by their lifting properties. And so this is a weak factorization system. And in particular, it gives me some kind of fibrant replacement. And because I don't require that the weak equivalences are the induced one anymore, like this kind of gives me a fibrant replacement already for free. So this condition kind of becomes trivial in this context. And instead, it's replaced by another condition, which requires that trivial fibrations are weak equivalences. So this is what this condition is saying, and let me explain it to you. So whenever I start with a trivial fibration, so a map that's mapped to a trivial fibration, then I need to find a commutative square as follows. So here, these maps are going to be maps in this left class determined by the preimage of the fibrations. And then I'm going to require that these objects are fibrants, by which I mean that the images are fibrant in N, or this should be N. Yeah, sorry. And so it's kind of like thinking of I'm replacing my X and my Y by fibrant ones. And then there is an induced map between these fibrant objects, which is in fact sent to a weak equivalence.
Why is there an induced map? Is that obvious?
This is just lifting property stuff. You know, like because this one is fibrant, then I have a lift because this one is in the left class. Yeah.
I see. Yeah.
So, but like I need just to find one squares that looks like this one and commutes such that the F prime is sent to weak equivalence. And this is like kind of saying trivial fibrations are weak equivalences. And as I was saying before, like we kind of want to induce the structure still between fibrant objects. And this is what happens in this context, namely a map between fibrant objects, so between objects such that Rx and Ry are fibrant in N, is going to be a weak equivalence of fibration if and only if it's in the preimage of the weak equivalence of the fibrations. So where it seems that we change a lot of things from the previous model structure, we still have that between fibrant objects, they kind of do the same. So between fibrant objects, we still have the induced weak equivalence and the induced fibrations. Okay. So
So
as
can
I
I
said
ask
before,
a question? Lynn, so do the methods in the proof of this theorem give you an explicit way of producing cofibrant replacements in this fibrantly induced model structure?
I mean, usually you start with, I mean, because the fibrations are the preimage of the, sorry, the trivial fibrations are the preimage of the trivial fibrations. Then the cofibration will be cofibranted generated by the image on the L of the set of cofibrations here. So if you want, you can use like this small object argument with respect to this set, and then you would get an explicit cofibrant replacement.
I see. So it's okay. It's as explicit as the small object argument permits, then. I see.
Yeah, and then in some cases you can simplify it a bit more, but like, yeah, there's no general result for this, I mean.
Okay, I see.
And so, as I said before, if the right-induced model structure exists, then it coincides with the fibrantly induced one. But in the example that we saw before, we had this adjunction, this inclusion of double categories into simplicial categories, where we put the ready model structure. And we saw that the right-induced model structure doesn't exist. But instead, what we showed is that the fibrantly induced one exists. And so this gives you an example where right induction failed, but fibrant induction works.
I have a question.
Yes.
Maybe I'm missing something, but so what are these two, like the right induced and the fibrant induced one, related at all?
Yeah, I mean, if the right induced exists, it coincides with the fibrant induced one.
Sure. But like, okay, never mind. I think I answered my own question.
Okay.
So was there a motivation for constructing a model structure on double categories?
I mean, this one is not very interesting, but it's kind of like, I feel like a leading example because Fiore, Planck, and Pauli really considered this, and then like they failed to construct it, and this is kind of fixing this theory. But like we have a lot of model structures on double categories actually, and I will mention some maybe in the applications afterwards. But yeah, for example, one of the things that are interesting to have model structures on double categories is to compare them with the infinity setting. So you have a notion of a double infinity category. And if you want to build a comparison between them, typically model categories are a good way of doing this. This is one example. And I don't know, it's as interesting as building model categories on n categories, for example, or two categories, I would say. Was that your question?
Yeah, that's okay.
Okay.
And is there a completely dual left induction result here as well?
Oh no, we don't know how to do this.
What
Because
what is the subtlety then? Like the right, I mean the right induction has a dual left induction, but now fibrant induction does not have a dual cofibrant induction.
I mean, you could define a cofibrantly induced model structure by, defining instead the trivial cofibrations and the cofibrant objects, I guess. But the thing is that like we don't have a dual of the theorem because if you look, for example, what Eskedirek, Real, and Shipley do in the left-induced case, they use this accessibility condition and this like algebraic weak factorization system to prove a similar theorem to the one I stated before for right induction. And so like proving this for left-induced model structure will require much more technology than the one we are using here. Because here we're using a lot combinatoriality, which is not very useful for left induction.
I see. So in the left in the right induction and left induction, the statements are dual, but the proofs are not dual. Is that what you're
Yes,
saying?
exactly.
I see. Good. So, but do you believe the methods can be extended for a
I
left
would
and
hope so, but yeah. I mean, it's becoming much more difficult than it was in this case, I would guess.
yeah. I remember already I tried to read the left induction proof once and it was complicated, I remember. Yeah.
Yeah, yeah, exactly. Okay. And so this right-induction theorem actually comes from a much more general method that we will develop, and actually it's a corollary of a more general theorem. And for this, I'm not gonna be starting from an adjunction, but this time I'm gonna be starting from a class of fibrant objects and a class of weak equivalences between them, and try to build a model category instead. So I will start with something that's locally presentable, and then I need to precise, first of all, a set of morphisms in my class. And because M is locally presentable, if you apply the small object argument, you get a weak factorization system, which is generated by J, so such that the right class is determined by the right lifting property against J. And here I'm denoting this weak factorization system with these letters because I want to think of the left-hand class as anodyne extension and the right-hand class as naive fibrations. And if you know a bit of Szynski model structure theory, he uses the same terminology, and this is kind of trying to reflect this because here we want to think of the anodyne extensions as some of the trivial fibrations, but not all of them. And the naive fibrations are going to be more than the fibrations, but they are still going to determine the fibrant objects and the fibrations between fibrant objects. So this is kind of like what these classes represent. And in particular, with this factorization system, I can define fibrant objects and fibrant replacements as I did before. So let me call an object X a naive fibrant if the unique map to the terminal object is a naive fibration. And so here I say naive fibrant, but in the end, they will be exactly the fibrant objects of the model structure. And then a naive fibrant replacement will be an anodyne extension from X to X prime, such that the target is naive fibrant. So these are like my fibrant replacements that I want to be. And so for the exact same argument as we had at the beginning of the talk, because we have a factorization system, then we can always factor any map as an anodyne extension followed by a naive fibration. And so in particular, if I apply this to the unique map to the point, I can show that naive fibrant replacements always exist. Okay, and so this is for the class of fibrant objects. And then I said I also want to precise a class of weak equivalences between my fibrant objects. And so this is what this WF is going to be about. So I just take any class of morphisms between naive fibrant objects. And then from this, I can define all of the weak equivalences because now I have fibrant replacements and I have weak equivalences between fibrant objects. And so I can define W to be the class of maps such that there is a naive fibrant replacement of that map that is in WF. So by this, I mean that I'm replacing my X with a naive fibrant one. I'm replacing my Y with a naive fibrant one. And then I have this induced map between the two naive fibrant objects, which is in my class. And so the theorem then states as follows. So first, I need to give some data. So I first want to precise a weak factorization system of cofibrations and trivial fibrations. And so here I just denoted this with this lifting properties, just to not confuse them with the actual trivial fibrations. And this is going to be generated by a set I. And then as before, I want to be given a set J, which is going to give me this anodyne extensions and naive fibration factorization system. And this class WF of maps between my naive fibrant objects. And now I want to build a model structure which has the following data. So the weak equivalencies are going to be defined exactly as I did here. And then the cofibrations are going to be the one that I picked. And the fibrations are going to be determined by their lifting property against trivial cofibrations. And so I want to ask, when does this model structure exist? The conditions are going to be the following. So first of all, I want W to behave as a class of invertible maps of weak equivalences. So I'm going to require it to have 2 out of 6, sorry, which is just like a weaker version of 2 out of 3. And there's also some accessibility condition that I don't really want to mention, but again, it's like a size control condition. And the second condition is going to be a path object condition, as we've seen before. So every time I start with a naive fibrant object, I can factorize my diagonal morphism into a map, which is in my class WF, followed by a naive fibration. And so here you can see that because X is fibrant, then the product is also naive fibrant. And so in particular, PX is also naive fibrant because this map is a naive fibration. So this is all well defined. This is indeed a map between naive fibrant objects. And then the next condition is, so I said before that I want the naive fibrations to be the fibrations between fibrant objects. And so this condition is kind of saying that if I have a naive fibration, which is also a weak equivalence between naive fibrant objects, then it is a trivial fibration. And often it's useful to have this set I, because then you can just check certain conditions that, certain lifting condition that this class of maps should satisfy in order to check that this is indeed the case.
So, Lynn,
and the last condition is that, yes?
Keep going, sorry. I'll ask my question at the end, yeah.
Okay, and the last condition is that trivial fibrations are also weak equivalences.
Okay, now can I ask my question?
Yes.
Yeah. All right. So do you want P, the path object, to be functorial, or this is something you don't need?
No, you don't need it. So actually, this condition is kind of equivalent to saying anodyne extensions between fibrant objects are weak equivalences, I think. But like you don't need any kind of functoriality for this to work.
Okay.
Okay, and so the last thing I wanted to say about this model structure is that we didn't build any model structure. We built one where between fibrant objects, it's really happening whatever we wanted it to happen. Namely, if I have a map between naive fibrant objects, then it's going to be a weak equivalence of fibration if it's in this class WF or a naive fibration. So this is really what we wanted to happen between fibrant objects. Okay, maybe I'll skip this part because I don't have, and I just want to mention some applications of these results. I mean, the part that I skipped is basically the proof that the fibrantly induced theorem follows from the general theorem. But yeah, I mean, it's in the notes if you want to look at it. So yeah. Okay, so I won't give much details about the applications. It's just like to show how useful this theorem has already been, and I'm hoping that there will be even more application in the future. And so the first example I'd like to give is about spectra. So you can look at the symmetric spectra, and then there is a forgetful functor to sequential spectra. On sequential spectra, I can put a stable model structure. And it's a well-known result that you cannot right-induce the model structure on symmetric spectra along this right adjoint. But what Malkiewicz and Sarazola have shown is that the fibrantly induced one actually exists. And so you can recover the usual stable model structure through this like right adjoint. And this gives a very short proof. I think it's like a 5-page paper or something like this of the existence of this stable model structure, which was really done by hand originally. Another example is kind of similar to the double categorical example I gave in the talk. And you can look, instead of just looking at internal categories to categories, you can look at internal categories into n categories instead. And then I can also look at graphs in n categories, and I have a forgetful functor. And here I can put a certain ready model structure again. And what we have shown is that the fibrantly induced model structure on internal categories to n categories exists. And if you look in the case n equals 1, this is really looking similar to what we had before, because we will have something induced from here. So before we had the whole simplicial complex, if you want, but now we're just truncating it. But this is a bit better from a homotopical perspective, because having the whole simplicial complex actually made some condition very strict, and there was some like existence of unique things, which is not very homotopical in practice. And so this is kind of fixing this other model structure I was talking about. And then we also have a lot of application of the more general theorem that I was telling you about. And first of all, we built, as I say, a lot of model structure on double categories. And actually in a work in progress right now, we're even building more of them. And one of these model structure was kind of the first one in the literature, which had a connection with two-category theory rather than just one-category theory. And so the idea was that like we build a model structure on double categories such that this embedding of two categories into double categories is equivalent functor. And another model structure that we built is one such that the square functor from two categories into double categories, which is basically saying a two category as a double category having the same horizontal and vertical morphisms is equivalent equivalent. So this gives like a homotopy theory on double categories, which is equivalent to that of two categories. Other examples include work with Maru Sarazola, and we built some model structure on the slice categories of category C. And so one of these model structure has as the fibrant objects the grothendieck fibrations of a C. And as you might know, this kind of aim to model functors valued into cat. And in fact, the grothendieck construction, so the usual one, from functors from C up to cat to this like slice category is going to be equivalent equivalence with respect to this model structure. And then we also have the discrete statement where you replace basically cat with sets. But this is a bit less interesting from the homotopy theoretic point of view because it involves sets, right? And one last example that I like to mention is work in progress with Joost Nuiten. And we put a model structure on simplicial spaces, but that still models infinity categories, but where the fibrant objects are not the complete Siegel spaces, but just the Siegel spaces. In fact, the completeness condition is kind of going into the cofibrant objects instead. And it's like a cofibrant object is going to be a simplicial space which has a homotopically discrete set of objects, space of objects, I mean. And yeah, it's indeed modeling infinity categories because it's equivalent to these complete Siegel spaces. Okay, and I guess I'll stop here. So thank you very much for your attention.
Let's thank Lynn. Okay, so are there any questions or comments? My main question is about so I have a few examples of adjunctions in which I would like to induce a cofibrantly induced model structure on the left-hand side. So
Yeah.
yeah, but I don't know if you have anything more to say about the possibility of doing this cofibrantly. Um, uh, I mean, what's exactly a technicality that one has to solve, or if you've thought about it?
No, I mean I haven't thought about it. I mean I think if you understand the methods of the Haskell-Turek Shipley paper, I think probably something similar would apply in this context. I'm hoping at least. And it would be nice to have the exact dual statement to the one I stated. So where like path objects are replaced with cylinder objects, and then trivial fibrations being weak equivalences would be replaced with trivial cofibrations being weak equivalences. But yeah, I mean, we haven't worked into this direction at all. So
Yeah. Okay. That's good. This was nice. Thank you. Are there any other comments or questions?
Yeah, can I ask that you like re-explain the idea behind this naive fibrancy? I think I got lost when you started that section.
yeah. Let me try to find it. I think it's yeah. Yes. So the idea is that like we want to have a factorization system which kind of tells us what the fibrant objects are and the fibrations between fibrant objects are. And maybe you know this result that like trivial cofibrations are determined by the lifting properties against fibrations between fibrant objects. And so it's kind of like just knowing these type of so fibrant objects and fibrations between fibrant objects is kind of like already telling you a lot about the model structure somehow. And so this is what this weak factorization system is about. So basically, you need to think of the naive fibrations as the fibrations between fibrant objects. So the naive fibrant objects are exactly the fibrant objects, and then the naive fibration are these like fibrations between fibrant objects. And this is kind of the idea behind this. And in particular, this factorization system is sufficient to get fibrant replacements. Because anodyne extensions are going to be, in particular, trivial cofibrations. And so like having this weak factorization system and being able to factor into an anodyne extension followed by a naive fibration already gives you access to fibrant replacements.
Maybe just because I haven't thought about this a lot. Can you say why you're calling it naive? Is it just because it's like vibrations between vibrant things?
I mean, the terminology doesn't come from me. As I say, it's
Okay.
like
Oh,
this.
I didn't know. I didn't know. Okay.
It's like this Szyczynski model structures, or like maybe you've heard it also in the context of the Dreier model structure. There are these anodyne extensions, and then
Right.
and then the right class with respect to anodyne extension is usually called naive fibrations.
I
And
see.
this is just like the terminology is borrowed from there, and I'm
Okay.
not sure why. I guess they call them naive fibrations because they were not the good vibrations.
Okay.
I have no no better answer, sorry.
Any other questions or comments? If not, let's thank Lynn again.
Thank you.